Okay, so here we go again. We have a quick video this time on bond enthalpies. You may remember the term enthalpy from year 10 when we did energy diagrams, where you're looking at exo and endothermic reactions. But we're not looking at anything that complex at the moment. When we talk about enthalpy, in this case, we're actually talking about energy. So let's have a look. When we're with bond enthalpies, we need a definition. Okay, so it's the amount of energy required to break a bond, and essentially that's about bond enthalpy. So the amount of energy we have to put in to break that bond. Okay, it's measured in a unit of kilojoules per mole, and we'll be covering the mole shortly, but basically that's the amount of energy in kilojoules required for a specific number of those bonds. And bond dissociation is basically that breaking. When we say dissociation, we're talking about breaking it apart. And this gives us quantitative evidence, okay, so a numerical value, that bond strengths vary because it takes different amounts of energy to break them in different molecules. Okay, so again, we're going back to that idea of experimental evidence. Okay, so if you think about this, and we talked about this a little bit already, that when we look at the bond length and how many bonds it has, so single, double, or triple, it makes sense that that would have an effect on the strength of the bond. Okay, if we think about it in the number of points that we have in gripping something, if we hold something with just one finger, it's not going to be very strong. 2 fingers, we get more grip strength, and so we can relate that back to our bond strength. And then 3 fingers, we're holding really tightly, so we have a much stronger grip. So essentially what we're looking at here is when we relate this to bond length, the more electron pairs that are involved in the covalent bond, the shorter the bond and the stronger the bond. And when we're talking about electron pairs, we're talking about our bonding pairs. Okay, so this is essentially the distance between the nuclei where we get the best attractive force. Okay, so where if we bring them too closely, they'll start to repel, but if they're just far enough apart, we get that great attraction, so it's where the strongest point will be in those 2 nuclei being attracted to each other. So the more electron pairs that we have, the shorter that distance is, because we've got more electrons between the 2 positive nuclei. Kind of makes sense. Okay, so back to this again. Okay, so when we look at this, so if we have 2 pairs of electrons, then we will have 4 electrons between the 2 nuclei, okay? And in the case of a triple bond, we've got 6 electrons between the 2 nuclei, okay? So the attraction is really good between those positive and negative charges, but we're preventing that repulsion of the two nuclei, which means that larger electron density gives us that stronger bond, but also draws them closer together so it's shorter. So just to recap that, basically what you need to remember is that the carbon-carbon covalent bond, and this is what we're talking about most of the time, okay, can exist as a single, double, or triple bond, okay? So when we're talking about as we increase the number of bonds, they get shorter and stronger. This is particularly what we're talking about, and we can see this here in that as our length decreases, okay, as our length decreases, our strength increases, okay? And you can go through this and have a look at it and refer to page 100 on your textbook to go through it, but that's pretty much what we need to know about bond enthalpies. And you can relate this back to other ones. If you think about the nitrogen bond, it's a triple bond, so it'll be strong, and our C double bond O in carbon dioxide, again, we would expect that to be quite a strong bond. So there's a number of examples that you can think of. I'll leave you to think of a few more.